Okay, this is going to be a little less than ideal, but this is the best I can do from home. So so I'm going to go through the notes that I've already posted online. So this is we're going to be looking at derivatives of exponential and logarithmic functions. So let's just remember what we already have. We already know that the derivative of any constant is 0. We know the derivative of x is 1. And we know that the derivative of x to the n is just n x to the n minus 1. And really, derivative of x falls out of this power rule as well. You don't have to remember them separately, but this is just an easy one to know. Okay, so now let's add in exponentials and logs. So let's first start with graphs. So we'll first start with y equals e to the x here. I don't think you can see that. Hang on a minute. Y equals e to the x, and y equals ln x. So y equals e to the x, remember, looks like this. It starts out with a kind of a gradual increasing slope and then starts to go up much more steeply. It goes through the value 1. Note that the slope is always positive, but it is increasing. Okay, now let's look at ln. It doesn't really come quite that flat. Okay, so a ln function, remember, is the inverse function for an exponential. It also has a positive slope, but it's increasing very steeply, and then it sort of shallows out. So let's think about then what the derivatives, we would expect the derivative to look like. So here, the derivative, it turns out to be just e to the x, the exact same thing. So if the function is e to the x, the derivative is e to the x. Very easy, and that makes sense because the function starts out with a small positive value and grows, and that's the exact same thing that the slope does. Let's look over here. The slope here, we said, starts out steep and then shallows out as x gets big. So it's kind of inversely proportional to x, and that's exactly what the derivative is. The derivative of ln x is 1 over x. So let's just do a quick example. I'm going a little bit out of order from the notes that I posted online, but we'll fix that up here shortly. So let's start with this one. If I know that y equals 4 e to the x plus 4x to the 2.7, I've purposefully put in one that's new and one that's not. Remember, multiplication by a constant and addition carry through. So when we go to do the derivative, the 4 carries down times the derivative of whatever that is. Derivative of e to the x is e to the x plus 4 times whatever the derivative of this is. That's a power. So remember, it's very important where the x is. Here, the x is in the exponent, that makes it an exponential, and here the x is in the base, that makes it a power function. So we bring the 2.7 down, and then subtract 1 from the exponent. So altogether we'll have 4 e to the x plus 10.8 x to the 1.7. Okay, so that's a good example of exponentials. So it's reasonable to expect that it will not always be this simple. So let's look at some important log rules that we need to remember. Exponentials tend to be pretty simple until we get to chain rule in a couple of classes. Logs are the ones that we can change now. So what we need to do first is look at some laws of logs. So some of these, you should have seen these in 163. Might be a little rusty if you haven't used them, so let's look at these. We know that if we have multiplication on the inside, I can rewrite that as 2 separate, simpler logs. So multiplication on the inside becomes addition on the outside. Similarly, division on the inside becomes subtraction on the outside. And then lastly, if we have ln a to a power, we can take that power and bring it down in front. So again, the whole purpose of this process is to take an inside that's more complicated than we know how to deal with and turn it into simple. Because remember, the only derivative we know is ln x. Not ln x squared, not ln x plus 2, quantity x plus 2, not anything more complicated yet. When we get to chain rule, we'll fix that. But for now, we only know very simple logs. So let's practice using these to simplify some logs. Let's do these examples. ln 2x cubed. All right, the first thing I see is there's multiplication, so I'm going to rewrite that as addition. Ln 2 plus ln x cubed. And then I see that I have this exponent. Remember, this can come down on in front, so I'll have ln 2 plus 3 ln x. Now, have I gotten to the simplest that I can get to? Yes, this is a simple ln x, nothing else. Remember that ln 2 is actually a number, so when I go to do the derivative of this, let's just do that. The derivative of this, the derivative of a single number is 0, plus 3 times the derivative of ln x, 3 over x. And if you're not quite certain how to work this out, you can always remember it this way. Multiply numerators, multiply denominators. Okay, let's look at another example. Ln 2x plus 3 over 4x plus 5. All right, I see division. So because I see division on the inside, I know I'll have subtraction on the outside. So this will be ln 2x plus 3 minus ln 4x plus 5. Now, it's important to note that I can't go any further than this. Addition on the inside is not something I can change. It's kind of like when you have square root of 2x plus 3. There's nothing you can do with that. This is most definitely not equal to the square root of 2x plus the square root of 3. Definitely not. Remember, you can really only deal with things that have multiplied factors. So if I had the square root of just 2x, I could write that as square root of 2 times square root of x. So multiplication on the inside we can deal with. Addition on the inside you can't change. So looking at this, this is not something we know how to take the derivative of yet because we don't have a plain ln x. So just we'll get there in a couple of classes. Okay, so now let's look at doing a more complicated derivative of a log. All right, so here's an example. This is example 3 in the notes. Okay, so if you have y equals 5 ln x minus ln x to the 7th. So the first thing I see is, okay, I'm looking at logs, so I need to find ln x. This one has a ln x, 5, multiplication by a constant, no problem. This one has ln x to the 7th. That's not the same thing. That's not simple enough. So I'm going to use this rule up here to pull that exponent down in front. So I'm rewriting. So anytime that you don't have plain ln x's, for now we need to rewrite. So 5 ln x minus 7 ln x. Well, they're all ln x's, right? Ln x. So they are actually, you can combine like terms. So you could write this as minus 2 ln x. If you don't see that, that's okay. You do the derivative of each piece, and then when you get down to the end, you'll see that there's some similarity you can combine again there as well. But it's easier to combine here. So if these are exactly the same, ln x and ln x, then you can combine them. So the derivative then, negative 2 times, that carries through. Negative 2 times, what is the derivative of ln x? 1 over x. So again, cleaning this up if you want to, if you need to, think about that as negative 2 over 1. Multiply numerators, multiply denominators. I'm going to put that minus sign out front. Remember, the negative sign can go in the front, in the numerator, or in the denominator. Only one place. Okay. Let's see. All right, so now we'll keep going and do another example. Here is example 4 from the notes. So I have f of x equals ln x cubed over 5. So the big question I need to ask if I'm looking for the derivative, is this a simple ln x? Clearly not. So I need to start to pull that apart to get down to a simple ln x. So the first thing I see is a division. So I'll start with just rewriting this. Ln x cubed minus ln 5. Are we down to plain ln x yet? Nope. I had ln x cubed. So again, I'm going to take this cubed, pull it down in front. So I'll get 3 ln x minus ln 5. Okay, now I'm ready to do the derivative. So I'm going to, let's see if I can write it down here a little bit better. The 3 comes down. 3 times the derivative of ln x, 1 over x, minus derivative of ln 5. Remember, ln 5 is a number. It's about, I'm going to write down 1.6 or so. So the derivative of any number is 0. So that means our final answer is 3 over x. Okay, so what do we know so far? We know that the derivative of e to the x is e to the x. Love that, very simple. Derivative of ln x is 1 over x. Again, very simple. Okay, so now we need to go, this is great if you have log base e or an exponential base e. What if you don't have a base e? That's not uncommon. So let's look at what we will do there. And here we're just, the derivatives will look very similar. We're just going to tweak them up a little bit. In fact, I will write them all up at the top together. So we have, just rewriting, okay, if it's not base e, if instead you have b to the x, so some other base, it will be the same pattern. The derivative is still b to the x. But now, because it's not base e, we have what I like to think of as a correction factor. So for example, if I want to define the derivative of 2 to the x, it'd be the same 2 to the x, the same exponential pattern, and then that's not a base e, it's a base 2, so ln 2. Okay, let's look over here at taking derivative of a log base b. So if I want to define the derivative of log base b of x. Again, ln would be base e, so this will be the same pattern, the same 1 over x, again times a correction factor, ln b in the denominator. So for b to the x, the correction factor is in the numerator. For log base b of x, the correction factor is in the denominator. And you can just memorize that. You can realize that, I guess the way that I think of it, try to remember it, is that because the variable's in the denominator, the correction factor is in the denominator, whatever you need to do. So if I had y equals log base 10 of x, then y prime would be equal to 1 over x, derivative of a log is 1 over x, times its correction factor, 1 over ln 10. So this is the new set of derivatives that you need to memorize. You need to have these for the Minute to Win It on Wednesday. So again, derivative of exponential is exponential, maybe with a correction factor. Derivative of log is inverse 1 over x, maybe with a correction factor. Okay, so let's do some more examples. All right, this is example, well, we kind of already did part of example 5, but let me just, I'm going to redo this one just to point out a difference. Y equals 2 to the x plus x squared. It is really important to pay attention to where the x is. There's a 2 and an x in each of these terms. Here, the x is in the exponent, that makes it an exponential. Here, the x is in the base, that makes it a power. So different rules entirely for derivatives. This is an exponential, so the derivative is an exponential times the correction factor. Here it's a power, so plain old power rule. Bring the 2 down in front, 2x. So just, it's very important to make that distinction. All right, let's look at example 6. Let's say we have h of x equals log base 5 of x plus log base 5 of 3x. Okay, so the question is this ready to find dh dt? I mean dh dx, sorry. Log of x, even with a different base, this is basic, that's ready. Log base 5 of 3x, this is not a plain x, so we are not ready. We need to rewrite this. So this is multiplication on the inside, so that becomes addition on the outside. So rewriting, we get log base 5 of x plus log base 5 of 3 plus log base 5 of x again. And again, this one and this one are identical, so we can combine them. 2 log base 5 of x plus log base 5 of 3. Okay, so now let's look at, now we're ready. This is just a plain log base x and log base 5 of x, and this is a number, like we talked about before. So dh dx 2 times the derivative of this. Well, that will be 1 over x. Derivative of log is always 1 over x, times its correction factor because we don't have base e, plus derivative of a constant is 0. So probably to clean it up, I would write it this way. And this is a good time to bring this up. Normally, remember, len 5 is a number. Normally, you know, if we have 2x, we write it 2x, we don't write it x2. But here, because if we were to write this instead, the constant on the front, it would look like that x was inside the len. So we don't write it that way. We'll put the variable in the front and put the len of the numbers following that. Okay. All right, so that's all of the new information. Now we're going to go and look at some applications, which wonder of wonders are exactly the same as the applications we've been doing before. So we're going to start with, oh yes, the equation of a tangent line. So equation of the tangent line to h of x equals 1 plus len x to the 4th at x equals 1. Don't let lens worry you when it comes to things like this. Just go ahead and just start doing some of the work. We do need to remember some things like len of 1 is 0, like e to the 0 is 1. There's some numbers that are easy to work with. So in this case, to find the equation of a line, what do we need? We need a point and we need a slope. We have the x point, so y we get from h of x. The slope we get from, because it's a tangent line, the slope is the derivative. Okay, so let's go ahead and start with y. So y will equal h of 1, because x is 1. So that's 1 plus len of 1 to the 4th is 1, len of 1 is 0. This whole thing is equal to 1. So that means we know that our point is 1, 1. Okay, we need the derivative. Is this ready to take the derivative? No, because this is not a plane x. We need to take this and put it down in front. So let's rewrite h of x. 1 plus 4 len x. So that means the derivative of 1 is 0. So that's 0 plus 4 times the derivative of len x, 1 over x. So h prime of 1, that would be the slope of the tangent line to this function at x equals 1 would be 4 over 1, 4. So we have our point and we have our slope. So y minus 1 equals 4 times x minus 1. Altogether y equals 4x minus 4 plus 1 minus 3. Yes. Okay, so that is finding the equation of a tangent line. It works exactly the same as it has been so far. It's just that now we have len x. You can do it with an e to the x function, same thing. Let's see, I'm trying to decide if I want to do, let's just set it up. Let's talk about this one. What if I have the same function, okay, and so we had the same derivative, and I want to know where is the tangent line horizontal? So remember what we have keywords here. Tangent line means that the slope is equal to the derivative. Horizontal means the slope is equal to 0. Combine these two, that says that the derivative is equal to 0. I want to find out what x value makes that true. Well, so grab our derivative, 4 over x equals 0. Is this ever true? No, never true. I could multiply both sides by x and I'd get 4 equals 0. Never true. So for this function, there's never a place where the tangent line is horizontal. All right, 2 more examples. Okay, I believe this one's in the book and I didn't write down which number it is. But so here's the example. It's about depreciation. So let's say the estimated resale value in dollars, R, of a company car depreciates. It loses value with time. I mean, we know that. We know that our cars are not worth what they were when we bought them. So we're going to say that the value, the resale value, is going to be the original value of the car times 0.86 to the t. So what does that mean? That means when t is 0, 20,000. Let's just do a couple of those. 20,000. When t is 1, 20,000 times 0.86. So it's only worth 86% of what it was the year before. And that pattern will continue. So this is saying that basically it's losing 14% of its value each year. Okay, so the question is, what is the instantaneous rate of depreciation after 1 year and after 3 years? So instantaneous rate. That should make you think automatically. Instantaneous rate. That tells you derivative. Okay, so what is this derivative? This is of the form b to the t, some number to the t. So it's an exponential. So we know that it 20,000 times, that stays in front. It's an exponential, so we have the same exponential in the derivative times the correction factor, ln of the base. Okay, so that's our derivative. So now if I want to find at 1 year, I just plug in, and at 3 years, I just plug in. So plugging in t equals 1 and t equals 3, I will get the values negative 2594 and negative 2231. Let's think about 1, why it's negative, and 2, does that make sense? Well, this value here is going to be negative. How do I know that? Because when I think about what the graph of a ln looks like, it goes through 0 at 1, and any number less than 1 is going to give me a negative y value. So I expect that to be negative. That makes sense because we're talking about depreciation. We're saying it's not worth as much, so we know it's losing value. So it makes sense that it's negative. Now let's talk about units. If you're not sure about units, the best thing to do is instead of writing r prime of t, write dr dt. And looking at this variable and this variable tell you your units. So r is in dollars and t was in years. So these answers would be this one depreciating at almost $2,600 per year, and here at $2,200. Does it make sense that the depreciation rate got lower? Yes. Look at the ln. I mean, I'm sorry, I need to come up here to the exponential. This was for computing that, but if I look at the original function, the exponential, because this is 0.86, it's actually going to be, it's going to look like that. And so it makes sense that it's a little bit steeper here and it starts to flatten out. So there's a greater depreciation at this point and then it gets less. How do I know it's this way? Because the base is less than 1. So if I have any b to the x where the base is greater than 1, it looks like this. Less than 1, less than 1, it's decreasing. Okay. Oh, one last thing I wanted to point out about computing with logs on your calculator. You will notice, I hope you already know this, but just in case, if you were trying to find 10 ln 2 on your calculator, that would be easy. You would just write 10 times, press the ln button, it will open a parenthesis for you, you put 2, you don't even have to finish the parenthesis, you're done. On the other hand, if you were trying to find this, you just change the order around and multiply by 10 on the back side. You would first press ln, it would open a parenthesis, you would type 2. You have to close that parenthesis before you multiply by 10. If you don't, it's going to assume that you're trying to find ln of 20. And 10 ln 2 and ln 20 are very different numbers. So just remember, if you have anything after the ln, you need to actively close the parenthesis that the calculator has opened for you. All right, here's our last application, and this one's about growth. Most of our applications tend to center around exponentials and not lns. Okay, so here's one, again from the book, I forgot to write down where. A single cholera bacterium divides every quarter hour to produce 2 complete bacteria. Wow, so we're doubling every 15 minutes we're doubling. If you start with a colony of 1,000 bacteria, then after T hours, this is what you'll have. So if you start with, so this is in hours, and this is the amount, A for amount. So you start with 1,000, and it's going to double every quarter hour. So that'd be T divided by 0.25. So when T is 0.25, I get 2 to the 1, I've doubled. When T is 0.5, I get 2 squared, I've doubled again. All right, so let's clean this up a little bit. We can then write this way. Dividing by 0.25 is the same as multiplying by 4. So I can change this to this. And now remember some laws of exponents. I can write this 1,000, and I can write that 2 to the 4th to the t. Or I could similarly write it 2 to the t to the 4th, but that's not very helpful here. So 2 to the 4th, that's 16. So 1,000 times 16 to the t. Wow, that's a big base. That's a big base. So now let's look at this. Let's find the derivative. So 1,000 times, well, first let's check, is this basic? Yes, 16 to the t, just plain t, so that's fine. So 1,000 times the derivative for this. So remember, the derivative of an exponential has that exponential form, but because this is not base e, we have to multiply by the correction factor. And so that is, I would leave it this way. Yeah, I don't see, I mean, I guess you could write that, I don't know what you would do. There's no great way to clean this up. Okay, so if we wanted to know what happens after 1 hour, what is the rate of change, we get 1,000 times 16 times ln 16, and this turns out to be 44,361. 44,361 watts. What are our units? Well, again, if we're looking at derivative, we can write dA dt. A is the number of bacteria, and T is hours. So this would be that many bacteria per hour. Wow, that's a huge increase at that point. All right, well, but let's look at what happens at 5 hours. You go ahead and plug in 5 for T, and it turns out you get sorry. Let's write the first one. 907 269 992 bacteria per hour. 2 billion bacteria per hour. So it is no wonder that cholera epidemics, when you have a cholera outbreak, it is a very bad and quickly moving problem because it multiplies so rapidly. Okay, so that's all I have. I'm just going to add one last bit for those of you who want a little bit more, and that is looking at, let's just reinvestigate this, the derivative of log base b of x. Well, we have something called a change of base formula. You may or may not remember that. I can rewrite that as ln x over ln b. That's just a change of base formula. That's actual, you know, it's just, that's what it's equal to. So if I want to take the derivative of this then, same thing, they're equivalent. Let's rewrite this again. Ln b is a number, so I could rewrite this as ln x times just this number, 1 over ln b. Okay, but when I take the derivative, this one becomes 1 over x times a constant that carries through, and there we go. There's the derivative of log base b of x using the change of base formula. Okay, that's all I have. That was a short one. Coming up next, on the next class, we're going to look at how to handle product and quotient rules. Let me just give you a little bit of that. Product rule, quotient rule.